The career that I started early on in my life was looking for exotic life forms in exotic places, and at that time I was working in the Antarctic and the Arctic and high deserts and low deserts until about a dozen years ago when I was really captured by caves, and I really refocused most of my research in that direction. So I have a really cool day job. I get to do some really amazing stuff. I work in some of the most extreme cave environments on the planet. Many of them are trying to kill us from the minute we go into them, but nevertheless, they're absolutely gripping and contain unbelievable biological wonders that are very, very different from those that we have on the planet. Apart from the intrinsic value of the biology and mineralogy and geomicrobiology that we do there, we're also using these as templates for figuring out how to go look for life on other planets, particularly Mars, but also Europa, the small icy moon around Jupiter, and perhaps someday far beyond our solar system itself. I'm very passionately interested in the human future on the moon and Mars particularly, and elsewhere in the solar system. I think it's time that we transitioned to a solar system-going civilization and species. And as an outgrowth of all of this, then, I wonder about whether we can and whether we even should think about transporting Earth-type life to other planets, notably Mars as a first example. Something I never talk about in scientific meetings is how I actually got to this state and why I do the work that I do. Why don't I have a normal job, a sensible job? And then, of course, I blame the Soviet Union. Because in the mid-1950s, when I was a tiny child, they had the audacity to launch a very primitive little satellite called Sputnik, which sent the Western world into a hysterical tailspin. And a tremendous amount of money went into the funding of science and mathematics skills for kids, and I'm a product of that generation, like so many other of my peers. It really caught hold of us and caught fire, and it would be lovely if we could reproduce that again now. Of course, refusing to grow up, even though I impersonate a grown-up in daily life, but I do a fairly good job of that, but really retaining that childlike quality of not caring what other people think about what you're interested in is really critical. The next element is the fact that I have applied a value judgment, and my value judgment is that the presence of life is better than no life, and so life is more valuable than no life. And so I think that that holds together a great deal of the work that people in this audience approach. I'm very interested in Mars, of course, and that was a product of my being a young undergraduate when the Viking landers landed on Mars. And that took what had been a tiny little astronomical object in the sky that you would see as a dot and turned it completely into a landscape as that very first primitive picture came rastering across the screen. And when it became a landscape, it also became a destination and altered really the course of my life. In my graduate years, I worked with my colleague and mentor and friend, Steve Schneider, at the National Center for Atmospheric Research, working on global change issues. We've written a number of things on the role of Gaia hypothesis, whether or not you could consider Earth as a single entity in any meaningful scientific sense. And then, as an outgrowth of that, I worked on the environmental consequences of nuclear war. So, wonderful things and grim things, but what it taught me was to look at Earth as a planet with external eyes, not just as our home. And that is a wonderful stepping away in perspective to try to then think about the way our planet behaves as a planet and with the life that's on it. And all of this seems to me to be a salient point in history. We're getting ready to begin to go through the process of leaving our planet of origin and out into the wider solar system and beyond. So, back to Mars. How hard is it going to be to find life on Mars? Well, sometimes it's really very hard for us to find each other even on this planet. So, finding life on another planet is a non-trivial occupation, and we spend a lot of time trying to think about that. Whether or not you think it's likely to be successful sort of depends on what you think about the chances of life in the universe. I think myself that life is a natural outgrowth of the increasing complexification of matter over time. So you start with a big bang and you get hydrogen, and then you get helium, and then you get more complicated stuff and you get planets forming, and life is a common planetary-based phenomenon in my view. Certainly in the last 15 years we've seen increasing numbers of planets outside of our solar system being confirmed, and just last month, a couple of weeks ago, a planet in the size class of Earth has actually been found. And so this is very exciting news. So my first bold prediction is that in the universe, life is going to be everywhere. It's going to be everywhere we look, where there are planetary systems that can possibly support it, and those planetary systems are going to be very common. So what about life on Mars? Well, if somebody had asked me about a dozen years ago what I thought the chances of life on Mars would be, I would have probably said a couple of %. And even that was considered outrageous at the time. I was once sneeringly introduced by a former NASA official as the only person on the planet who still thought there was life on Mars. And of course, that official is now dead, and I'm not, so there's a certain amount of glory in outliving your adversaries, but things have changed greatly over the last dozen years. And the reason that they have changed is because we now have new information. The amazing Pathfinder mission that went in '97 and the MER rover missions that are on Mars as we speak now, and the European Space Agency's Mars Express has taught us a number of amazing things. There is subsurface ice on that planet. And so where there is water, there is a very high chance of our kind of life. There's clearly sedimentary rocks all over the place. One of the landers is sitting in the middle of an ancient seabed. And there are these amazing structures called blueberries, which are these little rocky concretions that we are busy making biologically in my lab right now. So with all of these things put together, I think that the chances of life are much greater than I would have ever thought. I think that the chance of life having arisen on Mars sometime in its past is maybe 1 in 4 to maybe even half and half. So this is a very bold statement. I think it's there, and I think we need to go look for it, and I think it's underground. So the game's afoot, and this is the game that we play in astrobiology. How do you try to get a handle on extraterrestrial life? How do you plan to look for it? How do you know it when you find it? Because if it's big and obvious, we would have already found it. It would have already bitten us on the foot. And it hasn't, so we know that it's probably quite cryptic. Very critically, how do we protect it if we find it and not contaminate it? And also, even perhaps more critically, because this is the only home planet we have, how do we protect us from it while we study it? So why might it be hard to find? Well, it's probably microscopic, and it's never easy to study microscopic things, although the amazing tools that we now have to do that allow us to study things in much greater depth at much smaller scales than ever before. But it's probably hiding, because if you are out sequestering resources from your environment, that makes you yummy, and other things might want to eat you or consume you. And so there's a game of predator-prey that's going to be essentially universal, really, in any kind of biological system. It also may be very, very different in its fundamental properties, its chemistry or its size. We say small, but what does that mean? Is it virus size? Is it smaller than that? Is it bigger than the biggest bacterium? We don't know. And speed of activity, which is something that we face in our work with subsurface organisms, because they grow very, very slowly. If I were to take a swab off your teeth and plate it on a Petri plate, within about 4 or 5 hours, I would have see growth. But the organisms that we work with from the subsurface of Earth, very often it's months and in many cases years before we see any growth whatsoever. So they are intrinsically a slower life form. But the real issue is that we are guided by our limited experience, and until we can think out of the box of our cranium and what we know, then we can't recognize what to look for or how to plan for it. So perspective is everything, and because of the history that I just briefly talked to you about, I have learned to think about Earth as an extraterrestrial planet, and this has been invaluable in our approach to try to study these things. This is my favorite game on airplanes, where you're in an airplane and you look out the window, you see the horizon. I always turn my head on the side, and that simple change makes me go from seeing this planet as home to seeing it as a planet. It's a very simple trick, and I never fail to do it when I'm sitting in a window seat. Well, this is what we apply to our work. This shows one of the most extreme caves that we work in. This is Cueva de Villaluz in Tabasco, in Mexico, and this cave is saturated with sulfuric acid. There is tremendous amounts of hydrogen sulfide coming into this cave from volcanic sources and from the breakdown of evaporite minerals below the carbonates in which this cave is formed, and it is a completely hostile environment for us. We have to go in with protective suits and breathing gear, and 30 parts per million of H2S will kill you. This is regularly several hundred parts per million, so it's a very hazardous environment with CO as well and many other gases. These extreme physical and chemical parameters make the biology that grows in these places very special. Because contrary to what you might think, this is not devoid of life. This is one of the richest caves that we have found on the planet anywhere. It's bursting with life. The extremes on Earth are interesting in their own right, but one of the reasons that we're interested in them is because they represent really the average conditions that we may expect on other planets. So this is part of the ability that we have to try to stretch our imagination in terms of what we may find in the future. There's so much life in this cave, and I can't even begin to scratch the surface of it with you, but one of the most famous objects out of this are what we call snottites for obvious reasons. This stuff looks like what comes out of your 2-year-old's nose when he has a cold. And this is produced by bacteria who are actually making more sulfuric acid and living at pHs right around 0. And so this stuff is like battery acid, and yet everything in this cave is adapted to it. In fact, there's so much energy available for biology in this cave that there's actually a huge number of cave fish. And the local Soke Indians harvest this twice a year as part of their Easter week celebration and Holy Week celebration. This is very unusual for caves. In some of the other amazing caves that we work in, this is in Lechuguilla Cave in New Mexico near Carlsbad, and this is one of the most famous caves in the world. It's 115 miles of mapped passage. It's pristine, it has no natural opening, and is a gigantic biological, geomicrobiological laboratory. In this cave, great areas are covered by this reddish material that you see here, and also these enormous crystals of selenite that you can see dangling down. This stuff is produced biologically. This is the breakdown product of the bedrock that organisms are busy munching their way through. They take iron and manganese minerals within the bedrock, and they oxidize them. And every time they do that, they get a tiny little packet of energy. And that tiny little packet of energy is what they use then to run their life processes. Interestingly enough, they also do this with uranium and chromium and various other toxic metals. And so the obvious avenue for bioremediation comes from organisms like this. These organisms we now bring into the lab, and you can see some of them growing on Petri plates, and get them to reproduce the precise biominerals that we find on the walls of these caves. So these are signals that they leave in the rock record. Well, even in basalt surfaces in lava tube caves, which are a byproduct of volcanic activity, we find these walls totally covered, in many cases, by these beautiful glistening silver walls, or shiny pink, or shiny red, or shiny gold. And these are mineral deposits that are also made by bacteria, and you can see in these central images here scanning electron micrographs of some of these guys. These are gardens of these bacteria. One of the interesting things about these particular guys is that they're in the actinomycete and streptomycete groups of the bacteria, which is where we get most of our antibiotics. The subsurface of Earth contains a vast biodiversity, and these organisms, because they're very separate from the surface, make a vast array of novel compounds. And so the potential for exploiting this for pharmaceutical and industrial chemical uses is completely untapped, but probably exceeds most of the rest of the biodiversity of the planet. So, lava tube caves, I've just told you about organisms that live here on this planet. We know that on Mars and the Moon there are tons of these structures. We can see them. On the left you can see a lava tube forming in a recent eruption at Mount Etna in Sicily, and this is the way these tubes form, and when they hollow out then they become habitats for organisms. These are all over the planet Mars, and we're busy cataloging them now. And so there's very interesting cave real estate on Mars, at least of that type. In order to access these subsurface environments that we're interested in, we're very interested in developing the tools to do this. You know, it's not easy to get into these caves. It requires crawling, climbing, rope work, technical rope work, and many other complex human motions in order to access these. We face the problem of how can we do this robotically? Why would we want to do it robotically? Well, we're going to be sending robotic missions to Mars long in advance of human missions. And then secondly, getting back to that earlier point that I made about the preciousness of any life that we may find on Mars, we don't want to contaminate it. And one of the best ways to study something without contaminating it is to have an intermediary. And in this case, we're imagining intermediary robotic devices that can actually do some of that front-end work for us to protect any potential life that we find. I'm not going to go through all of these projects now, but we're involved in about half a dozen robotic development projects in collaboration with a number of different groups. I want to talk specifically about the array that you see on the top. These are hopping microbot swarms. I'm working on this with the Field and Space Robotics Laboratory and my friend Steve Dubowski at MIT. And we have come up with the idea of having little jumping bean-like robots that are propelled by artificial muscle, which is one of the Dubowski Lab's specialties, are the EPAMs, or artificial muscles. And these allow them to hop. They behave with a swarm behavior where they relate to each other, modeled after insect swarm behavior, and they can be made very numerous. And so one can send 1,000 of them. As you can see in this upper left-hand picture, 1,000 of them could fit into the payload bay that was used for one of the current MER rovers. And these little guys, you could lose many of them. If you send 1,000 of them, you could probably get rid of 90% of them and still have a mission. And so that allows you the flexibility to go into very challenging terrain and actually make your way where you want to go. Now, to wrap this up, I want to talk for 2 seconds about caves and the human expansion beyond Earth. As a natural outgrowth of the work that we do in caves, it occurred to us a number of years ago that caves have many properties that people have used and other organisms have used as habitat in the past, and perhaps it's time we started to explore those in the context of future Mars and the Moon exploration. So we have just finished a NASA Institute for Advanced Concepts Phase 2 study looking at the irreducible set of technologies that you would need in order to actually allow people to inhabit lava tubes on the Moon or Mars. It turns out to be a fairly simple and small list, and we have gone in the relatively primitive technology direction. So we are talking about things like inflatable liners that can conform to the complex topological shape on the inside of a cave, foamed in place airlocks to deal with this complex topology, various ways of getting breathing gases made from the intrinsic materials of these bodies. And the future is there for us to use these lava tube caves on Mars, and right now we're in caves and we're doing science and recreation, but I think in the future we'll be using them for habitat and science on these other bodies. Now, my view of what the current status of potential life on Mars is that it's probably been on the planet maybe 1 in 2 chances. The question as to whether there is life on Mars that is related to life on Earth has now been very muddied, because we now know from Mars meteorites that have made it to Earth that there's material that can be exchanged between those 2 planets. One of the burning questions, of course, is if we go there and we find life in the subsurface, as I fully expect that we will, is that a second genesis of life? Did life start here and was it transported there? Did it start there and get transported here? This will be a fascinating puzzle as we go into the next half century, where I expect that we will have more and more Mars missions to answer these questions. Thank you.